Our universe holds a secret woven into its very fabric. What if every point in space you see contains a hidden, tiny dimension curled into a perfect circle? A dimension so small it has escaped our notice for all of human history. This is the mind-bending proposal of Kaluza-Klein theory, a brilliant idea that suggests a fifth dimension could be the key to unlocking the deepest mysteries of reality. By the end of this journey, you will understand how a single, elegant geometric concept could unify the forces of nature and reshape our entire cosmic perspective. We will explore how light itself might be a vibration in this unseen realm and ask whether the true nature of reality is hiding in plain sight, just one dimension away. What does the shape of space itself tell us about our place in the cosmos? Einstein's theory of gravity was a monumental achievement, a new vision of the cosmos where the force we feel is simply the bending of space and time around mass. Planets orbit stars not because they are pulled by some invisible string, but because they are following the curves in a cosmic fabric. This idea of general relativity was breathtaking, explaining everything from the orbit of Mercury to the bending of starlight. Yet for all its power, this beautiful theory had a profound and frustrating limitation. It described only one of nature's fundamental forces. At the same time, James Clerk Maxwell's elegant equations perfectly captured another force, electromagnetism, portraying light as a traveling wave of electric and magnetic fields. Here was the dilemma. Einstein's gravity shaped the vast stage of the universe, while Maxwell's electromagnetism dictated the play of light and energy upon it. But the two sets of rules were written in completely different languages, with no connection between them. For physicists dreaming of a single, unified law for all of nature, this division was the great unsolved problem of their age. The universe was speaking with two separate voices, and the scientific community desperately wanted to hear one unified song. This was the intellectual frontier, the great puzzle that demanded a radical new solution, setting the stage for a brilliant and unexpected idea to emerge from the shadows. Into this intellectual stalemate stepped a quiet mathematician named Theodore Kaluza. Working in relative obscurity, he saw a path where others saw only a wall. Kaluza made a breathtakingly simple yet radical move. He took Einstein's equations for gravity, which described the warping of four-dimensional space and time, and rewrote them for a universe with 5 dimensions. The result was nothing short of magical. From the purely geometric fabric of this higher dimensional space, Einstein's equations for gravity emerged naturally. But then, something else appeared, an extra set of equations that perfectly described Maxwell's laws of electromagnetism. It was as if he had shown that gravity and light were not two separate forces, but merely different vibrations of the same 5-dimensional string. Overwhelmed by his own discovery, Kaluza wrote a letter to Einstein himself. The great physicist was initially captivated, calling the idea thoroughly original. Yet for 2 years, Einstein hesitated, wrestling with the proposal's physical meaning before finally supporting its publication. But the theory was still incomplete, a beautiful mathematical ghost without a physical home. Where was this 5th dimension, and why could we not see it or move through it? This is where Oskar Klein enters the story. A young physicist steeped in the new and bizarre world of quantum mechanics, Klein provided the crucial missing piece. He proposed that the 5th dimension was not a vast, open expanse like the others. Instead, it was curled up into a perfect, unimaginably tiny circle, a loop so small that it remained hidden from all our experiments. To understand this, picture a single, impossibly thin strand of hair. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself down to a subatomic scale and look closely, you would see the hair has a circular thickness, a second dimension that was always there, just hidden from your normal view. Klein argued our entire universe is like that hair, At every single point in the space around us, there exists this minuscule, circular fifth dimension. We are simply too large to perceive its curvature. With this elegant idea, the Kaluza-Klein theory was born, a unified vision of nature where the force of light is just gravity dancing in a hidden, compact dimension. Could the entire cosmos truly be built upon such a delicate, unseen geometry? But what does it truly mean for a dimension to be compactified? Think of a garden hose stretched across a vast field. From where you are standing, it looks like a simple line, a single dimension with only length. An ant crawling along that hose would experience only forward and backward movement, a one-dimensional existence. But you know something the ant does not. If that ant were to shrink down to a microscopic size, it would discover a completely new world. It could crawl not just along the length, but also around the full circle of the hose's surface. What appeared as a line was actually a cylinder, a two-dimensional surface that was curled up so tightly its circular nature was completely hidden from the large-scale view. This is the essence of compactification. The extra dimension is not missing. It is simply rolled up into a loop so incredibly tiny that its existence is beyond our normal perception. Our reality in the Kaluza-Klein view is that field. The three-dimensional space we move through is the long, visible length of the hose, and at every single point in that space, there is a fifth dimension curled into a circle billions of times smaller than an atom, a miniature loop we are forever tracing but never noticing. We are like giants living on the cosmic hose, completely unaware of the tiny, circular path available at our feet. This is not a dimension you can travel to in a spaceship. It is a fundamental part of space's geometry, a hidden fold in the fabric of the cosmos so small it has escaped detection, yet its potential influence on the universe could be profound. This hidden circular dimension is not just small, it is almost inconceivably tiny. Its proposed scale is the Planck length, a fundamental unit of nature so minute that it defies everyday comparison. To even begin to grasp its size, picture this. A single atom is to the entire observable universe as the Planck length is to that atom. This fifth dimension is curled up into a perfect circle with a radius on that unimaginable scale. It is a loop so profoundly small that our most powerful particle accelerators, which can probe distances a billion times smaller than an atom, are still utterly blind to its presence. We are trying to see the fine grain of wood while looking at an entire forest from miles away. So why do we believe such a thing could exist if we can never see it? The answer lies in the undeniable elegance of the mathematics. When you write down the equations for gravity in 5 dimensions and then tightly curl up that fifth dimension, the physics we observe in our 4 familiar dimensions naturally emerges. The force of electromagnetism is not something added to gravity. It is simply the part of 5-dimensional gravity that vibrates along the hidden circular path. Light itself becomes a gentle ripple in the geometry of this tiny coiled dimension. Think of a guitar string. When you pluck it, it vibrates to produce a musical note. That note is not a separate entity from the string. It is a property of the string's vibration. In the very same way, the electromagnetic force is the fundamental note played on the string of the compact fifth dimension. This is the profound beauty of the Kaluza-Klein proposal. It suggests that the universe achieves a deep unity not by adding more complexity, but by revealing a hidden simplicity woven into the geometry of space itself. All of reality might be the direct consequence of how dimensions, both vast and vanishingly small, are folded together into a single, coherent whole. The true magic of this idea unfolds within the mathematics itself. We begin with a universe of 5 dimensions governed by a single, elegant law, Einstein's equations of gravity. There is no separate force of electromagnetism here, only the pure geometry of a 5-dimensional space. Then we perform the crucial step. We tightly curl that 5th dimension into a tiny circle. This act of compactification is like applying a cosmic filter to the equations. As the circle shrinks, the single, unified mathematical description of five-dimensional gravity begins to split apart before our eyes. One part of it stretches out, remaining sensitive to the vast, familiar dimensions of length, width, and depth. This part becomes, with perfect fidelity, Einstein's original theory of general relativity, governing planets, stars, and the curvature of space-time. But the equations have a second part, a remnant that is entirely tied to the properties of the tiny, coiled circle. These leftover components, born from the geometry of the compact dimension, arrange themselves with stunning precision. They are not a new invention, they are James Clerk Maxwell's complete equations for electromagnetism. The electric field, the magnetic field, the very nature of light itself, all emerge as inevitable consequences of gravity vibrating along a hidden, circular path. Think of it like a single beam of pure white light passing through a prism. The prism does not create the colors, it merely separates them, revealing the rainbow that was always contained within the original beam. In the very same way, compactifying the fifth dimension acts as a mathematical prism. It takes the unified white light of five-dimensional gravity and separates it into two fundamental colors, the deep red of gravitation and the brilliant blue of electromagnetism. The miracle is that both forces were always different facets of a single, deeper geometric truth. This is not a clumsy merger of two separate ideas. It is the revelation of a hidden unity, showing that the universe might use a simpler, more beautiful language than we ever dreamed. So light itself gains a breathtaking new identity. It is no longer a mysterious wave traveling through empty space, but a direct vibration, a rhythmic pulse in the very geometry of that hidden fifth dimension. Every flash of light, from the glow of a distant star to the beam from your phone, is essentially a tiny, circular dimension breathing in and out. This is the ultimate promise of the Kaluza-Klein vision, that the fundamental forces are not forces at all in the traditional sense. They are the natural music of space-time, played on instruments of different sizes. Gravity is the deep, resonant bass note from the vibrations of our large, familiar dimensions. Electromagnetism, and the photon that carries it, is the higher-pitched melody arising from the tight, rapid oscillations along the minuscule circle. We are surrounded by this cosmic symphony, but we have only just begun to hear the full orchestra. What other instruments, what other dimensions might be playing a part in the harmony of the universe, waiting for us to discover their subtle tune? This hidden circle is so minuscule that our very language struggles to describe it. We call its size the compactification radius, a term for the distance from the center of the circle to its edge. To grasp this scale, consider a proton, one of the particles at the heart of every atom. A proton is already vanishingly small, but the proposed radius of the fifth dimension is thought to be a billion times smaller than that. If a proton were expanded to the size of our entire solar system, this compactified circle might only be as large as a single house on Earth. This is the realm we are talking about, a scale where the normal concepts of space and time begin to break down. Our most powerful machine for probing reality, the Large Hadron Collider, smashes particles together with incredible force. Yet even the tremendous energies it creates are like using a planet-sized hammer to try and detect the subtle texture of a snowflake. The collider probes distances 1,000 times smaller than a proton, but to see the direct effects of a curled-up dimension, we would need energies trillions of times greater, far beyond any technology we can even conceive of today. The vibrations in that tiny dimension, which manifest as photons of light, are so gentle and low energy that we perceive them perfectly. But to actually detect the circular shape itself, to feel its curvature, we would need to create a vibration so powerful it would wrap around the entire circle, a feat requiring energies that dwarf anything in our universe since the first moments of the Big Bang. So the fifth dimension hides not by magic but by sheer mind-numbing scale. It is a secret written in script too fine for our current eyes to read, a fundamental note in the cosmic symphony that is played on a string too small for our instruments to find. What other profound truths about reality might be concealed just beyond the edge of our perception, waiting for a future generation to develop the tools to listen? Oskar Klein saw a universe buzzing with quantum possibility. While Kaluza had laid the geometric foundation, it was Klein who realized that the theory remained silent on a crucial question. What about matter itself? The strange new science of quantum mechanics was revealing that particles like electrons were not just tiny balls, but also possessed wave-like properties. Klein wove this quantum thread directly into the fabric of the compactified dimension. He proposed a simple yet revolutionary idea. Imagine an electron existing not just in our three dimensions, but also moving within that hidden, circular fifth dimension. According to quantum rules, the wave describing this electron would have to wrap around the tiny circle in a very specific way. It could only vibrate in complete, whole number cycles, fitting perfectly into the circumference like a standing wave on a looped string. This quantum constraint, this requirement for a whole number of wavelengths, has a direct physical consequence. It quantizes the electron's momentum as it travels along the circular path. And here lies the breathtaking connection. Klein's equations showed that this quantized momentum in the fifth dimension is exactly what we observe and measure as electric charge in our familiar four-dimensional world. An electron has a specific negative charge because its quantum wave is vibrating in a particular, allowed pattern around the hidden circle. A proton has its positive charge because its wave is wrapped in a different, opposing way. The very property that defines how particles interact with light, their electric charge, is not some arbitrary tag assigned by nature. It is a direct readout of their hidden motion in a higher dimensional realm. Electric charge becomes a form of cosmic momentum, a silent memory of a particle's journey through a dimension we cannot see. This transforms our understanding of reality. The fundamental building blocks of matter are not just inhabitants of space, they are intimately shaped by its hidden geometry. Their most essential properties are literally written in the way their quantum waves resonate within the curled-up folds of the cosmos. Could all of physics be this elegant, a simple consequence of vibrations in a universe with more dimensions than we ever suspected? This elegant vision of a five-dimensional cosmos, however, soon met a harsh and unyielding reality. The dream of a complete unification, where gravity and electromagnetism were the only forces, was shattered by discoveries unfolding within the atom itself. As physicists probed deeper into the atomic nucleus in the 1930s and 40s, they encountered not one but two entirely new and powerful forces. The strong nuclear force was discovered, an immensely powerful glue that binds protons and neutrons together against their tremendous electrical repulsion. Without it, every atomic nucleus in the universe would instantly fly apart. Alongside it was the weak nuclear force, responsible for a certain type of radioactive decay and the nuclear processes that power the sun. These were not minor additions, they were fundamental pillars of nature, as essential as gravity and electromagnetism, and the original Kaluza-Klein theory, in its beautiful simplicity, had no room for them. Its five-dimensional geometry could elegantly produce two forces, but the universe was now revealing it needed at least four. The theory, which had promised to be the final chapter in physics, suddenly looked like an incomplete first draft. It was a beautiful failure, a masterpiece of mathematical elegance that described only half the known universe. The single, unified song physicists had hoped to hear was now a cacophony of four distinct voices, and Kaluza-Klein's five-dimensional symphony could only account for two of them. The theory was not wrong, it was simply insufficient. It was like devising a perfect theory of color, only to discover that the world also has sound and smell and touch. The scientific community, with a new and more complex reality to explain, largely set the idea aside. the hidden circle remained a fascinating footnote, a brilliant but ultimately inadequate map to a cosmos that was far more complicated than anyone had dreamed. For decades, the Kaluza-Klein dream lay dormant, a beautiful relic in the attic of physics. Yet its core idea was too powerful to fade away entirely. The notion that extra dimensions could be compactified, hidden from view, was a seed waiting for the right conditions to sprout again. That revival came with the rise of string theory, a radical new framework that sought not just to unify forces, but to describe the very fabric of reality itself. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. And for the mathematics of these vibrating strings to make any sense, to produce the rich tapestry of particles and forces we see, they require more than just the 3 dimensions of space and 1 of time that we experience. They need extra dimensions. The ghost of Kaluza-Klein had returned, not as a solitary 5th dimension, but as a whole new architecture for the cosmos. The simple, elegant circle was no longer enough. The new theories demanded a more complex hidden geometry. Instead of 1 extra dimension, string theory suggested there could be 6 or 7 of them, all curled up together at every point in space. But these are not just 6 separate circles. They are woven into intricate multi-dimensional shapes known as Calabi-Yau manifolds. To grasp this, think back to the garden hose. A single curled-up dimension is like that simple cylinder. Now, try to envision a shape with 6 different dimensions all curled up into a single, unified object. It is a form that exists in 6-dimensional space, a shape with holes and handles, with curves and tunnels, a geometric sculpture of breathtaking complexity. We cannot picture this shape directly, just as a flat, 2-dimensional drawing cannot truly capture the depth and form of a 3-dimensional statue. But we can understand its purpose. The specific, intricate geometry of this Calabi-Yau manifold determines how the strings vibrate within it. And just as the single circular dimension in Kaluza-Klein theory gave rise to the photon, the vibrational patterns of strings on a Calabi-Yau manifold give rise to the entire particle zoo. The electron, the quarks, the neutrinos, and even the carriers of the strong and weak nuclear forces all emerge as different resonant notes played on the strings wrapped around this hidden geometry. The failure of the original theory to include these forces was not a flaw in the compactification idea itself, but a limitation of its simplicity. By expanding the hidden realm from a single circle to a rich, 6-dimensional landscape, string theory attempts to complete the unification that Kaluza and Klein began. The charge of an electron, the mass of a quark, the very number of generations of matter, all of these fundamental properties of our universe may be locked into the topology of these invisible, curled-up dimensions. We are living in a universe whose physical laws are dictated by the shape of something we can never see. The search for a theory of everything has become, in many ways, a search for the one true Calabi-Yau manifold whose geometry sings the exact symphony of our reality. This leap from a single circle to a multidimensional Calabi-Yau manifold is like the difference between a simple musical note and an entire symphony. The circle gave us the photon, a single particle of light. But to get the entire cast of characters in the universe, from quarks to electrons, we need a stage with far more intricate geometry. A Calabi-Yau manifold is that stage. It is not one hidden circle, but 6 or 7 extra dimensions all curled and woven together into a single, stable shape. We can attempt a crude analogy. Picture a tiny, multifaceted gem, but one where every facet is itself a surface that curves and connects in higher dimensions. This gem has holes like the holes in a donut, but these are multidimensional tunnels and voids. Its topology, the number of these holes and the way its surfaces are connected, is not random decoration. This geometry is everything. Think of the strings of string theory as the universe's most fundamental violin strings. A Calabi-Yau manifold is the body of the violin. The shape and size of a real violin's wooden body determine which notes resonate richly and which fade away. In exactly the same way, the precise geometry of a Calabi-Yau manifold dictates exactly how the fundamental strings can vibrate. One specific pattern of vibration on the manifold might correspond to an electron. Another, slightly different resonance might be an up quark. The mass of the particle, its electric charge, and even more exotic properties are all determined by the string's vibrational mode, which is itself a direct product of the hidden geometry. In this profound sense, the Calabi-Yau manifold is like the cosmic DNA of our universe. Just as your DNA contains the blueprint that dictates your physical form, the specific Calabi-Yau shape compactified at every point in space could hold the blueprint for all physical law. It tells the strings how to vibrate and therefore dictates what particles can exist and how they can interact. A different choice of Calabi-Yau manifold with a different number of holes or a different curvature would produce an entirely different set of vibrational patterns. This would be a universe with different fundamental particles, different forces, and potentially no atoms, no stars, and no life. The profound question then becomes not why our universe has the laws it does, but why it is built upon one specific Calabi-Yau shape and not another. Is our cosmic DNA the only possible option, or is it just one possibility in a vast, unseen landscape of realities? This beautiful geometric vision of the cosmos, however, leads us directly to its greatest scientific challenge. If these extra dimensions are so perfectly hidden, so fantastically small, how can we ever prove they are real? A theory that cannot be tested risks becoming a beautiful piece of philosophy rather than a description of our actual universe. This is the central criticism leveled against compactified dimensions and the theories they inspire. For an idea to be scientific, there must be a conceivable experiment that could, at least in principle, prove it wrong. So where do we even begin to look for evidence of something that exists at a scale a billion times smaller than a proton? The search has pushed experimental physics to its absolute limits, forcing scientists to devise incredibly clever ways to probe the fabric of reality. One of the most dramatic approaches involves our most powerful microscope, the Large Hadron Collider. The hope was that by smashing particles together with unprecedented energy, we might not see the extra dimension directly, but we could witness its shadow. The theory suggested that if enough energy were concentrated in a tiny space, some of that energy could momentarily leak into the compactified dimension, curling up to form a microscopic black hole. This tiny, fleeting object would instantly evaporate in a burst of characteristic particles, a clear and unmistakable signature of new physics. It would be like striking a cosmic gong so hard that it rings in a hidden chamber we never knew existed. Researchers at the Collider have searched tirelessly for this telltale signal, sifting through the debris of countless collisions. So far, the micro-black holes have not appeared. The hidden chambers have remained silent, suggesting that if extra dimensions exist at the scale we were hoping for, they are even smaller and more tightly curled than our most optimistic models predicted. Another, more subtle line of inquiry looks not for new objects but for subtle failures in our oldest force. Newton's law of universal gravitation and its refinement in Einstein's theory tells us that the force of gravity weakens with the square of the distance. This is the famous inverse square law. But what if that law breaks down at incredibly tiny scales? The reasoning is elegant. In our familiar 3 dimensions, gravity's influence spreads out like the surface of an expanding sphere, naturally diluting its strength according to the inverse square. However, if there are extra, compact dimensions, gravity could have more directions in which to spread at very small distances. At a scale comparable to the size of the curled-up dimension, gravity might begin to seep into this hidden geometry, causing its strength to drop off faster than the inverse square law predicts. It would be as if a faint whisper of the force were leaking into a parallel room, making it slightly quieter in our own. To test this, physicists have built exquisitely sensitive experiments that measure the gravitational attraction between objects placed mere micrometers apart. These are not easy measurements. They must be performed in a vacuum, isolated from the slightest vibration, and shielded from the electrostatic forces that easily overwhelm gravity at such tiny scales. The goal is to see if gravity behaves exactly as expected all the way down to distances far smaller than the width of a human hair. Any deviation would be a monumental discovery, a crack in the classical facade revealing the hidden architecture beneath. So far, gravity has held firm to the inverse square law at every scale we have been able to probe. Yet the search continues with new experiments planned that will push into even more minute realms. The fact that we have not yet found evidence does not mean the idea is dead. It means the hidden dimensions, if they are there, are even more elusive than we imagined. They remain a ghost in the cosmic machine, a whisper of a possibility that continues to drive the most ambitious experiments in human history. What if the greatest secret of the universe is not just small, but is waiting for us to become clever enough to ask the right question? The origin of the compact dimensions is a mystery buried in the universe's first fleeting moments. In the fiery dawn of the Big Bang, all of reality was compressed into an inconceivably hot, dense state. At that primordial instant, the very concepts of size and dimension may have been fluid. Some cosmologists hypothesize that in that initial chaos, all dimensions were on an equal footing. The three spatial dimensions we know were just as small and curled as the extra ones proposed by Kaluza and Klein. For a fraction of a second after creation, our entire cosmos might have been a perfectly symmetrical, multidimensional knot. Then a pivotal event occurred known as cosmological symmetry breaking. A single, random fluctuation tipped the scales. For reasons we do not fully understand, three of those dimensions were singled out. They underwent a breathtakingly rapid expansion, inflating in an instant to become the vast, observable universe we inhabit today. Meanwhile, the remaining dimensions, perhaps 6 or 7 of them, failed to catch that inflationary wave. They remained tightly wound, frozen at the Planck scale, their intricate Calabi-Yau shapes becoming the hidden bedrock of physical law at every point in the now expanding cosmos. This idea transforms our picture of the Big Bang. It was not just the beginning of time and the expansion of space, but a dimensional sorting event, a cosmic process that selected which dimensions would become the grand stage of galaxies and which would become the hidden script governing the players. The universe we see is simply the part that got away, the fraction of reality that expanded while the rest remained compact, dictating the rules from behind the curtain. Could the specific pattern of the cosmic microwave background, the oldest light in the universe, hold a faint imprint of this dramatic separation, a whisper from the moment the dimensions chose their fate? This leads to another profound possibility. What if the compact dimensions were not always so small? An alternative vision suggests that in the very first instant, all dimensions were large. The universe was a truly higher dimensional place. Then, as it cooled and evolved, the extra dimensions became unstable. Picture a marble rolling down a steep hill into a deep, narrow valley. The higher dimensional state was the top of the hill, a precarious position. The compactified state, with its tiny, stable circles and manifolds, was the valley floor, a state of lowest energy. The universe, seeking stability, rolled down that hill, and the extra dimensions collapsed, curling up into their modern, hidden form. This process of dimensional reduction would have been a cataclysmic event, releasing a tremendous amount of energy that could have been pumped directly into the three dimensions that remained large, fueling their explosive inflation and shaping the large-scale structure we see today. The distribution of galaxies across the sky might be a fossilized record of how the cosmos folded in upon itself. The drive for a unified theory of physics therefore becomes inseparable from the story of our cosmic origins. To understand why the universe is the way it is, we must ask not just what the hidden dimensions are, but how they were born, how they evolved, and why they chose to hide, leaving us with a reality that is both vast and veiled. This hidden geometry may not be the only way to conceal dimensions. A more radical and cinematic idea has emerged, suggesting our entire universe is a three-dimensional island adrift in a higher dimensional ocean. This is the brane world scenario. In this model, our cosmos is not just embedded in higher dimensions, it is a membrane, or brane for short, a vast dynamic surface where all known particles and forces except one are trapped. The matter that makes up our bodies, the light from our screens, the nuclear forces in the sun, all are confined to this three-dimensional brane, like images painted on a soap bubble surface. They cannot leave the brane, which is why we only directly experience three spatial dimensions. But what about gravity, the force that shapes the cosmos? In this picture, gravity is different. It is the one force not confined to our brain. It can leak out, spreading through the full volume of the higher dimensional realm called the bulk. This single idea offers a stunningly simple explanation for one of physics' oldest puzzles: why gravity is so incredibly weak compared to the other forces. A magnet the size of a coin can lift a paperclip, defying the gravitational pull of the entire Earth. Why is gravity so feeble? In the brane world, the answer is dilution. The gravitational field our brain produces does not remain concentrated on our surface. It bleeds out into the vastness of the bulk, its strength thinning and spreading across dimensions we cannot access. The gravity we feel is just the tiny fraction that remains, the faint echo of a force that has mostly leaked away into a hidden realm. This transforms the compactified circle from a feature of space into a feature of our own cosmic identity. We are not just creatures of three dimensions, we are inhabitants of a specific membrane, a slice of reality with its own unique set of physical laws. And if our brane exists, what is to stop others from floating in the bulk? The possibility of parallel universes becomes not just a philosophical speculation, but a direct consequence of the geometry. Other branes could exist mere millimeters away from us in the higher dimensional bulk, yet be completely invisible because their light and matter are trapped on their own membrane, unable to cross the gap. We could be floating right next to a completely different cosmos, separated not by vast reaches of space, but by a dimensional barrier we cannot cross. The only force that might bridge the gap is gravity. A cataclysmic event in a neighboring brane, like the collision of two stars, could send a ripple of gravitational waves through the bulk, a ghostly signal that might one day wash over our world, a whisper from a universe next door. The idea that our physical laws might be dictated by hidden geometry leads to a staggering question. Could a civilization far more advanced than our own ever learn to reweave that cosmic fabric? Imagine a future where humanity, or some other intelligence, graduates from merely understanding the universe to actively engineering its deepest layers. The ultimate technology would not be a faster engine or a more powerful laser, but a tool to adjust the very shape of the compactified dimensions that define reality. Such a civilization would not just use the laws of physics, it would possess the master key to rewrite them. The first and most profound application would be the manipulation of fundamental constants. Think of the fine structure constant which governs the strength of electromagnetism or the mass of an electron. In the Kaluza-Klein and string theory picture, these are not arbitrary numbers handed down from on high. They are direct outputs of the geometry of the Calabi-Yau manifold. The size of its holes, the lengths of its curves, the angles of its folds, all these topological features translate directly into the numbers we measure in our particle accelerators. An engineer of dimensions would have the power to tune these values. They could dial the strength of the electromagnetic force up or down, perhaps to create materials with impossible properties, or to forge stars with new and stable nuclear pathways. They could adjust the mass of fundamental particles, potentially creating entirely new forms of matter that are currently forbidden by nature's settings. This goes far beyond chemistry. It is the ultimate programming of reality, with the compactified geometry acting as the universe's operating system. The user interface for such a technology is almost beyond our ability to conceive. It would not involve screwdrivers or wrenches, but fields and energies of unimaginable precision, applied to space-time itself to gently reshape its hidden folds. The energy required to pry open a dimension, even for a moment, would dwarf the output of galaxies, demanding a mastery over cosmic power sources we can only dream of. Yet, if such control were ever achieved, the resulting technologies would be indistinguishable from magic. A society that could reshape compact dimensions could, in principle, invent new forces. They could engineer a Calabi-Yau manifold with an extra vibrational mode, creating a new fundamental interaction that does not exist in our natural universe. This new force could be tailored for specific purposes, perhaps a form of cohesion that allows for the construction of objects that are truly unbreakable, or a new type of field that enables propulsion by directly manipulating the fabric of space, rendering rockets and fuel obsolete. Communication could occur instantaneously across any distance by exploiting the non-local connections within the higher dimensional bulk, making our current concept of the Internet seem as primitive as smoke signals. The very act of engineering dimensions would blur the line between the natural and the artificial. What would it mean to encounter a star system that glows with a light of a color never before seen in nature, because the local value of the fine structure constant has been artistically adjusted? Could there be cosmic gardeners who cultivate regions of space with different physical laws, creating pocket universes as diverse as ecosystems on Earth? This is the horizon of speculative physics, a future where the hidden architecture of reality becomes the ultimate canvas for intelligence. While this remains firmly in the realm of distant possibility, it forces us to see the cosmos in a new light. The universe may not be a fixed set of rules, but a dynamic and potentially malleable structure, waiting for a consciousness advanced enough to understand its blueprint and pick up the tools. The energy required to pry open a hidden dimension is not just large, it is cosmically prohibitive. To actually probe the geometry of a compactified circle, you would need to create a vibration so powerful that it wraps all the way around the tiny loop, a fundamental excitation known as a Kaluza-Klein mode. The energy needed to create this single, detectable vibration is determined by the size of the dimension itself. Since the proposed radius is on the order of the Planck length, the energy required is the Planck energy, a number so vast it defies all human-scale comparison. To put this into perspective, the Planck energy is approximately 10 quadrillion times the energy achievable in our most powerful machine, the Large Hadron Collider. It is the energy equivalent of the entire mass of a small asteroid, compressed and unleashed in a single subatomic event. This is not the energy output of a power plant, or even of all the world's nuclear arsenals combined. This is energy on a stellar scale. To gather enough power for just one attempt to tickle a hidden dimension, you would need to harness the total energy output of our Sun for millions of years. The device itself is almost a secondary concern, a hypothetical trigger for a cataclysm. The true engineering challenge is the power source, a civilization-scale project of literally astronomical proportions. This staggering requirement is precisely why these dimensions remain hidden. They are not just small, they are protected by an energy barrier so immense that it places them far beyond the reach of any technology we can envision. The universe has effectively locked its deepest secrets away in a vault, and the key requires the power of a star. What kind of intelligence could ever amass such power, and what would it mean for a species to graduate from manipulating matter to reshaping the very dimensional fabric of reality itself? Our daily commute would become a journey through geometry itself. Instead of navigating the long, winding roads of three-dimensional space, your vehicle would slip into the higher dimensional bulk, taking a shortcut through a direction that simply does not exist on any map. A trip from New York to Tokyo would not be a flight across the Pacific, but an instantaneous hop, as the vast distance in our three dimensions becomes a trivial gap when viewed from a higher vantage point. This is not faster than light travel, it is something far more profound, a complete bypass of conventional space. The very concept of a traffic jam would vanish, replaced by a seamless flow through a dimension where proximity is redefined. Communication would undergo a similar revolution. Our current signals, whether radio waves or fiber optic light, travel through our three-dimensional brain and can be intercepted or jammed. But a message sent through the bulk, vibrating through the compact dimensions themselves, would be inherently secure. It would be like whispering through a solid wall, your voice appearing on the other side without ever traveling through the air in between. To anyone confined to our three-dimensional reality, the transmission would be completely undetectable, a secret passed through a hidden corridor of the cosmos. This would not just create perfect encryption, it would forge instantaneous connections across any distance, linking colonies on Mars or explorers in distant star systems as if they were in the same room. The delay and distortion of our current networks would become a relic of a more primitive age. Our homes and tools would be transformed by dimensional engineering. A power source could tap directly into the vibrational energy of the Calabi-Yau manifold, drawing a tiny fraction of the infinite energy stored in the quantum jitters of the compact dimensions. Your personal device would not be a phone or a computer, but a dimensional resonator, a tool that gently tweaks the local geometry of space to manifest whatever you need. Need light? It would coax a specific vibration from the hidden manifold, filling the room with photons. Need to assemble an object? It would orchestrate the fundamental forces, guiding particles to coalesce into form from the raw potential of the vacuum itself. Manufacturing and recycling would lose all meaning, as matter itself becomes a temporary pattern in the higher dimensional symphony, easily composed and dissolved. Even our perception of reality would shift. With the right interface, you might learn to perceive the higher dimensional landscape directly. The compactified dimensions would no longer be abstract equations, but a rich, tactile geometry overlaying your vision. You could see the intricate folds of space-time, the hidden tunnels and handles of the Calabi-Yau manifold at every point. A simple wall would appear as a complex, multi-dimensional structure, and you would intuitively know which vibrational pathways could safely carry you through it. This would be the ultimate augmentation of human experience, not just adding data to your sight, but granting you a fundamentally new sense, the ability to see the cosmic code that writes reality itself. In such a world, the line between the physical and the informational would blur completely. The universe would reveal itself not as a collection of separate objects, but as a single, dynamic, multi-dimensional entity, and we would finally be awake to its true, magnificent shape. Discovering a hidden dimension would be more than a scientific triumph, it would be a cultural earthquake. History shows us that when our map of reality changes, everything we believe about ourselves changes with it. Copernicus moving Earth from the center of the universe did not just rearrange the planets, it dethroned humanity from a position of cosmic privilege. Darwin's theory of evolution did not merely explain the origin of species, it wove us into the tapestry of all life, removing us from a separate act of divine creation. Each of these revolutions was initially met with resistance not because the math was wrong, but because the implications were so deeply unsettling to our self-image. The confirmation of an extra, curled-up dimension would be the next great upheaval. It would tell us in the most concrete terms possible that the world we perceive is a fraction of the whole. Our senses, which we rely on for every fact of our existence, are not just limited, they are fundamentally incomplete, blind to an entire axis of reality. This realization would ripple through every layer of human thought, from philosophy and art to our most personal sense of meaning. How would our concept of God or a creative force evolve if we understood the universe was built upon a geometric scripture written in hidden dimensions? Could spirituality and science find a new common ground in the language of cosmic geometry, where the divine is not a watchmaker in the sky, but the architect of a magnificent multidimensional fabric? For centuries, these two ways of understanding the world have often been framed as being in conflict, one relying on faith and the other on empirical evidence. But what if the evidence itself points to a reality of profound, hidden depth, a cosmos with layers of elegance and unity that transcend our everyday experience? The awe one feels looking at a starry night could be magnified a billion-fold by the knowledge that each point of light is a nexus of unimaginable geometric complexity. This would not reduce the universe to a cold set of equations, but could infuse it with a new kind of sacredness, a majesty based on the verifiable beauty of its hidden architecture. Our place in the cosmos would be simultaneously humbled and exalted, smaller in our physical scope, but vastly greater in our potential to comprehend the true nature of existence. We would no longer be just inhabitants of a universe, but students of its deepest, most intimate secrets, forever unraveling the folds of a reality far grander than we ever dreamed. This new vision of reality would inevitably spill over into our creative spirit. Architecture, the art of shaping space for human experience, would face its most radical revolution. How do you design a building when you understand that every point within its walls is a gateway to an unseen, multi-dimensional landscape? Architects would become geometers of the invisible, crafting structures that resonate not just with our three-dimensional senses, but with the hidden folds of space itself. A simple corridor would no longer be a mere passageway. Its design could incorporate subtle materials and energy fields that gently interact with the compactified dimensions, creating rooms that feel larger on the inside, not through trickery, but by allowing your perception to brush against the extra geometric volume. Staircases might not just lead upward, but could be designed to guide you along a gentle curve in a fourth spatial dimension, arriving at a destination that seems spatially disconnected from its starting point. These would be buildings of impossible geometry, where walls could be both solid and transparent depending on the vibrational frequency of the light you use to view them, a direct application of how different energies couple to the Calabi-Yau manifold. The very concept of a window would transform. Instead of a pane of glass looking onto a street, a window could be a portal that lets you peer not into another place, but into another dimensional aspect of your own room, observing the intricate light and shadow play of higher dimensional shapes. Art would undergo a parallel metamorphosis. For centuries, painters have struggled to represent three-dimensional depth on a two-dimensional canvas. How would an artist portray 4, 5, or 11 dimensions? New art forms would emerge, perhaps using holographic projections that twist and turn in ways that are topologically forbidden in 3 dimensions, creating sculptures with Klein bottle shapes that have no inside or outside. Composers could write music based not on harmonic frequencies alone, but on the vibrational spectra of hypothetical Calabi-Yau manifolds, translating the hidden geometry of the cosmos into a symphony that the human ear can finally hear. The most profound impact, however, would be in the realm of virtual reality. Our current VR constructs a convincing simulation of 3 dimensions. A future simulation built with an understanding of compactified geometry would be something else entirely. You would not just put on a headset, you would step into a universe with its own physical laws. In this immersive reality, you could reach through solid objects by moving your hand along a compactified direction. You could solve puzzles by rotating entire rooms in 4 dimensions, seeing all sides of an object at once. This would be more than a game. It would be a training ground for intuition, a place where the human mind could slowly learn to grasp the reality it inhabits. The very act of creation would become a collaboration with the universe's hidden blueprint. Artists and architects would no longer be just shaping matter. They would be composing with the fundamental forces, painting with light born from hidden vibrations, and designing spaces that acknowledge the full, magnificent, and multi-dimensional truth of existence. The games of tomorrow would be less about pixels on a screen and more about geometry in your hands. A simple puzzle game would challenge you to guide a particle not just left and right, but also along the circular path of a compactified dimension. You would need to rotate the particle's quantum phase, feeling its momentum shift as its effective charge changes in your three-dimensional view. Success would depend on your intuitive grasp of a hidden direction, turning abstract physics into a tangible skill. Entire worlds could be built around navigating Calabi-Yau manifolds. Imagine an adventure where you explore a vast, dark cave, but your only tool is a device that emits vibrations at different frequencies. To proceed, you must find the resonant frequency that matches a specific hole in the local manifold's geometry, causing a hidden tunnel to shimmer into existence. A wall that is utterly impassable in 3 dimensions might have a large, open gateway in the 4th, visible only to those who can perceive the full dimensional landscape. Victory in these games would not be about quick reflexes, but about achieving a state of dimensional fluency, learning to see the world as it truly is. Cinema would undergo its own revolution, moving beyond 3-dimensional effects to portray the geometry of reality itself. A filmmaker could guide the audience's perception through a 4th spatial dimension, showing a character turning a sphere inside out without tearing it, or escaping a locked room by simply stepping sideways into a direction we cannot normally access. The visual language for this would be entirely new. An object might be shown from multiple 3-dimensional perspectives at once, its full 4-dimensional form slowly becoming clear to the viewer's mind. The plot of a thriller could hinge on a murder committed in a higher dimension, leaving a clue that is a topological knot, impossible to tie or untie in our limited space. These stories would not just be entertainment, they would be a form of mass education, training our brains to comprehend the profound possibilities hiding within the fabric of space. This new reality would inevitably birth new physical sports, demanding a complete redefinition of athleticism. A stadium for the sport of bulk ball would be a vast, open volume, not a flat field. Players, equipped with suits that allow limited movement through the higher dimensional bulk, would compete in a game where the ball can suddenly vanish from one location and reappear in another, having taken a shortcut through a compactified direction. The strategy would be a dizzying blend of 3-dimensional positioning and 4-dimensional anticipation, reading the gravitational ripples in the bulk to predict the ball's impossible trajectory. Another sport might resemble 3-dimensional chess played with real pieces in a volumetric arena, where capturing an opponent's piece involves not just surrounding it, but moving around it in a hidden dimension. The athletes of this future would possess a spatial intelligence we can barely conceive of, their bodies and minds perfectly synchronized to navigate a cosmos of greater depth. In this world, play itself becomes the most profound way to understand our place in a multi-dimensional universe. This ghostly matter could be the most direct evidence of a hidden dimension. For decades, astronomers have known that galaxies spin so fast they should tear themselves apart. Yet something invisible holds them together, a cosmic glue we call dark matter. We see its gravitational pull on stars and gas, but it emits no light and refuses to interact with any particle we know. All our attempts to detect it directly have failed, leaving one of the greatest mysteries in science. But what if the solution is not a new, exotic particle, but a simple matter of geometry? The brane world model offers a breathtakingly elegant answer. Imagine our entire universe is one 3-dimensional membrane, and just a microscopic distance away in a higher dimensional bulk, there floats another brane, a parallel universe. On that neighboring brane, there could be stars, planets, and galaxies made of ordinary matter, just like our own. The matter on that other brane would have its own light, its own chemistry, its own life, completely separate from ours. The crucial point is that all the forces except gravity are trapped on their home brane. The light from that other universe cannot cross the gap to reach our eyes, and their atoms cannot bump into our atoms. But gravity, which leaks through all dimensions, can. The gravitational pull from the stars and planets on that parallel brane would seep into our space, acting as an invisible, pervasive source of mass. To us, it would appear exactly as dark matter does, a ghostly gravitational influence with no visible source. We would be feeling the weight of a whole other cosmos brushing up against our own. This idea transforms the dark matter problem from a search for a missing particle into a question of cosmic architecture. We are not missing matter, we are simply blind to the matter that is right next to us, separated by a dimensional curtain. The mysterious substance shaping the cosmos might be nothing more than the ordinary stuff of a parallel reality, so close we could almost touch it, yet forever hidden by the very laws of physics. This cosmic architecture of hidden folds and intricate geometry inevitably leads us to a profound and unsettling possibility. The sheer mathematical elegance of a universe built upon compactified dimensions feels less like a random accident and more like a piece of brilliant engineering. When we look at the universe, we see a system of stunning efficiency where complex forces emerge from simple geometric principles, and where the laws of physics appear to be written in a language of perfect logic. This observation brings us face to face with the simulation hypothesis, the idea that our reality is not base reality, but an incredibly advanced construct, a cosmic computer program. In this light, the compactified dimensions of Kaluza-Klein and string theory take on a startling new role. They are no longer just a theoretical curiosity, they could be the ultimate optimization feature. Think about the computational power required to simulate an entire universe. Every particle, every force, every point in space would demand an astronomical amount of data processing. But what if the programmers found a way to simplify the code? A fundamental technique in computer graphics and video game design is level of detail. When an object is far away from the viewer, you don't render it in high resolution. You use a low detail model to save processing power. Compactified dimensions could be the universe's version of this technique. Why simulate a vast, expansive fifth dimension when you can achieve the same physical effects by curling it up into an unimaginably tiny loop? The properties of that loop, its radius and geometry, would then determine the fundamental constants of our reality, like the charge of an electron or the strength of light. This is not a bug, it is a feature, a memory-saving compression algorithm of breathtaking sophistication. The fine-tuning problem in physics, the mysterious fact that dozens of physical constants have just the right values to allow for stars, planets, and life, has long puzzled scientists. From a simulation perspective, this fine-tuning is not a miracle. It is simply the initial parameter setting chosen by the programmers. They dialed in the values for the compactification radii of the extra dimensions, and our universe, with all its specific laws and particles, booted up. We are not living in a universe of infinite possibilities, but in one very specific build defined by a particular set of geometric parameters. The search for a theory of everything, the one equation that describes all of physics, is then the quest to reverse engineer the source code. Every time a physicist writes down an equation describing a Calabi-Yau manifold, they are not just doing abstract math, they might be reading a line from the universe's fundamental program. The haunting question then becomes, if we are in a simulation, what lies outside the simulation? Is the bulk, the higher dimensional space in which our brain floats, simply the server room, the base reality where the computer running our universe physically exists? And if we one day unlock the secrets of dimensional engineering, would we be hacking the system, gaining the ability to rewrite the very code that defines our existence? The power to reshape reality is the ultimate form of authority, and with it comes a responsibility that could dwarf our collective wisdom. Imagine a future where a single error in dimensional engineering does not just cause a local explosion, but triggers a catastrophic chain reaction in the compactified geometry. An unstable universe would not be a distant philosophical concept, but a tangible threat. A miscalibrated field meant to adjust the fine structure constant could instead cause the Calabi-Yau manifold to unravel, its intricate folds collapsing or expanding in an unpredictable cascade. This would not merely change the laws of physics in a lab, it would rewrite them across a volume of space, potentially creating a bubble of alien physics that expands at the speed of light, erasing atoms and chemistry from existence as it grows. The very stability of the vacuum, the foundational state of our universe, could be compromised, turning a region of space into a cosmic dead zone where matter as we know it cannot form. The frightening truth is that the first sign of such a disaster would likely be its arrival, an irreversible wave of nothingness sweeping across star systems. This is not a risk contained to a single planet, it is an existential threat on a galactic scale, where one experiment gone wrong could silence the cosmos. Who would have the right to take such a gamble, and who would be qualified to grant that permission? Beyond the risk of accidental annihilation lies the more immediate and human danger of weaponization. If you can tune the compact dimensions to strengthen electromagnetism, you could also create a device that locally disables it. A weapon that simply turns off the electromagnetic force in a region would cause every atom in its target to instantly disintegrate as the bonds holding electrons to nuclei and atoms to each other vanish into nothing. There would be no explosion, no debris, just the silent and instantaneous dissolution of matter into a cloud of disconnected subatomic particles. Alternatively, a dimensional resonator could be tuned to vibrate a specific Calabi-Yau mode, exciting a particular type of matter. A city's worth of silicon or carbon or even the water in human bodies could be made to resonate with destructive energy, boiling or tearing itself apart from the inside out. Such weapons would be undetectable by conventional means, striking from a direction that does not exist in three-dimensional space, with no projectile to intercept and no radiation to shield against. The very concept of a battlefield would become meaningless as conflict could be waged from a hidden dimension against which there is no possible defense. The balance of power would shift from nations who control nuclear arsenals to those who hold the master key to physics itself, creating a potential for tyranny and oppression unlike anything in human history. Perhaps the most profound schism, however, would be the one that splits humanity itself, the gap between those who can perceive and manipulate the multi-dimensional fabric of reality and those who are confined to the old, three-dimensional world would be unbridgeable. This would not be a simple educational divide like the gap between a doctor and a laborer. It would be a fundamental difference in perception, a chasm in the very experience of being. The dimensional engineers would live in a world of rich geometric depth, seeing the hidden tunnels and vibrational pathways that structure existence. They would communicate through the bulk, perceive time as a mutable dimension, and possess an intuitive understanding of causality that seems like magic to everyone else. The rest of humanity would be left in the flatland, unable to even comprehend the tools and technologies that now govern their lives. How could a person who cannot perceive a fourth spatial dimension possibly participate in a democracy that votes on dimensional policy? How could they hold accountable leaders who operate on a plane of reality they cannot access? This could create a new class system, not based on wealth or birth, but on cognitive and perceptual capacity, potentially leading to a world where a small elite of dimensional masters governs a vast population of perceptual serfs. The unity of the human experience would shatter, replaced by a hierarchy defined by who can see the true shape of the cosmos and who remains forever blind. The quest to understand the universe's deepest secrets could ultimately reveal the most painful truth of all. the fragility of our own shared humanity. From a quiet mathematical proposal in the 1920s, this idea has grown into a foundational pillar of modern physics. The journey began with a single, elegant circle, a hidden dimension curled into a loop too small to see. That simple geometric shape promised to weave together the fundamental forces of nature, revealing gravity and light as two different expressions of a single, deeper reality. It was a dream of cosmic unity born from pure geometry. Though the original theory could not contain the full complexity of our universe, its core principle did not die. It was reborn, more vibrant than ever, within the ambitious frameworks of string theory and brane worlds. The single circle expanded into a landscape of intricate Calabi-Yau manifolds, shapes whose hidden folds might dictate every law of physics, every particle of matter. This progression from a solitary dimension to a complex cosmic architecture shows a profound truth: that the most powerful ideas in science are often the simplest and most beautiful at their core. They are seeds that can lie dormant for decades, waiting for the right moment to blossom. The concept of a hidden dimension has evolved from a curious solution into a key that could unlock everything from the mystery of dark matter to the origin of the Big Bang itself. It challenges our perception, suggesting that the true nature of reality is not in what we see, but in the intricate, invisible geometry that structures the void. This is more than theoretical physics. It is a new way of seeing our place in the cosmos. We are not just living in a universe of 3 dimensions, but within a delicate and dynamic multidimensional fabric, a masterpiece of hidden origami. The potential is staggering, hinting at a future where understanding this geometry could lead to technologies that reshape reality, redefine travel, and rewrite the very laws of nature. It all started with a circle, so we turn this final question over to you. Which part of this hidden universe captures your imagination the most? Is it the elegant idea that light is just gravity dancing in a 5th dimension? The haunting possibility that dark matter is the gravity from a world next door, or the profound thought that our entire cosmos might be defined by the shape of an unseen 6-dimensional gem? Share your thoughts, because the next great discovery in physics might just begin with a single curious mind.